Hello everyone, welcome to your online lecture on Mechanics of Materials 2. So for this lecture, we are going to discuss deflection of beams, more specifically singularity functions. So under deflection of beams, we have four topics. We already finished the first two. So the first one is deformation under transverse loading. So in this topic, we discussed second order differential equation, fourth order differential equation, and then the main objective is to get the equation of elastic curve. Now for the second topic, statically indeterminate beams, the main objective is to calculate for your support reactions. Now in this case, let's say you have four different unknown forces and you can only generate three equations. So it's not solvable, so you have to get another equation to solve your problem. So you can use your second order differential equation from this topic right here, or fourth order differential equation. Use the boundary condition to solve for your support reactions. So the third topic right here is singularity function to determine slope and deflection. So we discussed this topic last lecture. So we defined what's singularity function. We started solving the problem. However, we never finished that problem. So we're going to solve that one. But before we move to the example, let's have a quick review about singularity functions. So the main objective is to use a single mathematical expression to represent shear and bending moment. So if we talk about singularity function, so I'm going to drag my whiteboard right here. For singularity function, we talk about that could be expressed by x minus a, and that's a notation for your singularity function and raised to n. Now x is the length of your beam A is the position of your force or your moment. Position of force or moment. And then your N is the behavior of your force or moment. Behavior of force or moment. Now, how can we describe this if we have a beam? So let's say we have a beam with length of x. So we have a beam and we know that this is x right here. Now, if we have a force P, so let's say this is force P, we can define the location of force P by having point A, or sorry, distance A. Now that would be your A, so that describes the location of your P. Now how about your N? So before we discuss the significance of this N right here, first let's draw the shear and bending moment diagram. So which are this? Shear. Just going to change the color of my pen to red. Let's see. Okay. So now let's draw our shear and moment diagram. So note that this beam, it's not really in equilibrium. So from P, so we have a negative value right here. We have this guy right here. So this is going to be your shear. Note that it will not go to zero because it's not in equilibrium. So we have this value of our shear. Now for our moment, it's a negative slope, which means from this point, we have something like this, which is negative. Now for singularity function, we can describe the behavior of our curve. What do we mean by behavior? It's this guys right here. Now if we're going to write a singularity function for this one, we can define a straight line, just like this one, as x minus a raised to 0. Now if we have a diagonal line, we can say that this is x minus a raised to 1. Now if we have, for example, Just going to flip it a little bit. So let's say we have something which looks something like this, which is a power of 2. We can say that this is x minus a raised to 2. Now we can summarize this one by having this diagram right here. Let's draw a line here. So let's say we have from 0 to x, and then we have a plot which looks something like this. This is defined by x minus a raised to 0. Now if we have something like this from 0 to x, if we have something like this is a right here, it's a, that could be defined by x minus a raised to 1. And if we have something like this, again 0 to x, we have, it starts from here, so that's point A again, we have x minus a raised to 2. Now we also discussed last time that we can treat a singularity function as your variable if you're going to perform integral or differentiation. So let's say we want to get the integral of x minus a raised to n dx. So we treat this as our x or as our variable. So for this one, we are going to get 1 over n plus 1 x minus a, and this would be n plus 1. And if we're going to, for example, get the derivative of that same function, so let's say we have d over dx of x minus a raised to n, that's going to be equal to n x minus a and minus 1. And again, we have this notation for your, let's change the color. So we have this notation for your singularity function. So it's not your regular parenthesis if you have a, for example, if you have your equation. So that's how we treat our singularity functions. So if we go back to our slides, I'm just going to flip this one up. Okay. Now if we go back to our slides, so this table right here summarizes the singularity function if you have different types of forces or moment. So let's say if we have a moment right here. So if we have a moment at specific point of your beam, there's no associated shear with that. There's some moment right there, and it's defined by this singularity function here. Now, same thing for our force. If we have force, which is just a concentrated load P, so we have specific shear. We have this equation right here, negative P. So if your force is going down, that's going to be negative P right there. And then you have your x minus a raised to 0. So that's this line right here. And now from your shear, going to your moment, it's now a diagonal line, which means your n is equal to 1. In this case, you have negative p, and then you have your x minus a raised to 1. If you have distributed load from A up to the end of your beam, so you have first, you have your diagonal line, so that's raised to 1, and then eventually you're going to have a curve. Now this is raised to 2, and so on. So this is a triangular distributed load. So k would be your slope, so that's k, that's negative k over 2. Same thing here, if you have a certain w raised to n, so that's n plus 1, and then n plus 2. So that's how we use singularity functions. And for singularity functions, we have to isolate each moment, each force, or each distributed load, and make a separate singularity function for those loading type of loading. So I'm going to drag again my screen. Now, if we have a singularity function, So again, let's go back to our example, which is x minus a raised to n. Now there's two values that it could assume. The first value is either it's x minus a raised to n, so that would be your conventional equation. So we change the singularity function sign into your regular equation signs. Sorry. So you have this, you change it into parentheses there, just to take note of that. Or you can have another value which is equal to 0. Now you can assume the first value if you have x is greater than or equal to a. What do we mean by this condition? X is greater than or equal to a. That would mean that this value right here would be positive or 0. Now how about if we have a 0 value right here? That would happen if you have x is less than a. What do we mean by x is less than a? That would mean that this value right here would be negative, which means the overall value of your singularity function ranges from 0 up to a positive number, but it doesn't assume a negative values. Now that's for this specific singularity function. How about if we have x minus a and then raised to 0? Now, as we know, for a regular number, anything raised to 0 is equal to 1. But in this case, it could assume two different values, which is 1 or 0. How can we get 1? So we have a value of 1 if our x is greater than a. And that would mean that if this value x minus a is positive, that would mean we will get a value of 1 for this specific singularity function. How about for a 0? Now, if our x is less than a, that would mean that this x minus a value would become negative. So we're going to get 0 value for that specific singularity function. But the next question is, what if our x is equal to a? That would mean that the value x minus a would be equal to 0. And if that's the case, we can either assume it's 0 or 1. But in our class, we're going to use a 0 value for this specific condition. Now that we discussed what is singularity functions, how to interpret singularity functions, so let's have an example so that you can see how we can apply these concepts right here in obtaining the equation of your elastic curve. I'm just going to flip it up and then move to next slide right here. Now let's go to concept application number 1. So find the equation of elastic curve using singularity functions. So let's say we have a beam, we have a force P right here. It's from L over 4 from point A. And okay, so first, I'm going to put it here. Let's write the beam. I'm going to maximize that later. So first, let's draw our beam. So we have our beam, that's A. It's point A. So we have rollers here. So that's our B. And then this is going to be your P. This is L over 4. And then this is 3L over 4. Yeah, so that's our beam. Now we can call point A, we can call that as our AY, and at B, we can call it as our BY. I'm going to maximize it. So again, the question is find the equation of elastic curve using singularity functions. So the first thing that you have to do is to get all the forces on your beam. So if we're going to get the forces on our beam, so we have this is our beam, change the color. So we have AY, by, then we have our p. Now, if you're going to calculate your ay and by in terms of p, eventually what you will get here is a is equal to 3 over 4p, and your by would be equal to 1 over 4p. Now, you have all three different forces here, so 3 over 4p, 1 over 4p, and then you have your p right there. Now we can get our singularity function to describe this specific loading condition. So how can we get our singularity functions? So again, if we remember the second order differential equation or fourth order differential equation, our objective is to get, for example, shear in terms of x, or we can have moment in terms of x, and then we can integrate our function to solve our problem. So in this case, let's say we want to take the shear in terms of x using singularity functions. So first, we have to look at different forces or moments one by one. So let's look at the first force right here, which is 3/4 p. Now, this is going up, which means it's positive. So how did I know it's positive? So if we look in the table right here, so we have V, that's your negative P. So if your force is going down, your P right here, it's negative. But our force, AY, it's going up, which means P is a positive number. X is just your X. A is the location of your force. In this case, your A is 1/4 L, which means I could write my singularity functions in order to describe this loading condition here. Okay, so let's do that. Okay, oops, sorry. Okay. Now we have 3 over 4p. Sorry, the distance is not 1/4p, it's 0 because we are talking about AY. So 3 over 4p, and then we have our singularity function x minus 0, and then that's raised to 0. So that's for shear, and this is 0 right here. This guy is 0, it's because this point right here is 0. So that's your 0 value there. Oh, sorry, not that one. Let's go to erase. It's for this guy right here, sorry. Okay, so it's for this 0 right there. Now we move to our second force, which is P. So your P is going down, which means it's negative P. X minus the location of your force, in this case it's 1 over 4 L raised to 0. Again, how did we find that it's 1/4 L? That's the location of your force right here. So I'm just going to drag this 1/4 here to this guy. Now that's your 1/4 L. And then how about the third force that we have? So that's going up, which means it's positive. So which means it's positive 1 over 4p singularity function x minus, now that's located at L raised to 0. So that would be your shear in terms of x. How about if we're going to take our moment? So our mx, I'm just going to rewrite this one down here. Flip it up. So for your moment in terms of x, again, we have to look at forces or moment individually. So in this case, let's look at moment. So yeah, for your moment singularity function, it's defined by this equation right here. Negative p x minus a raised to 1, and it's negative if it's going down. So let's do it here. Maybe I'll a little bit. So now for your m, first let's look at the first force, which is 3 over 4p. So we have 3 over 4p. 3 over 4p. And then our singularity function is x minus 0 raised to 1. Now that's the first. We move to the second force, which is p right here. So we're going to write negative p. Now we have x minus 1/4 L raised to 1. So that's your second term. And then you're going to have your third term, which is 1/4 p. So we have plus 1/4 p x minus L raised to 1. So we have this moment equation. And if we talk about, again, the equation of elastic curve, we always want to get m in terms of x, because we know that we have d squared y dx squared is equal to mx over ei. In this case, we now have a singularity function which is in terms of x. However, we can further simplify this equation right here. It's just showing you that we acquired this mx because we need this equation right here in order to describe our or define the equation of our elastic curve, which is y as a function of x. That's our ultimate goal. Now let's analyze this moment the moment equation right here, and probably we can further simplify this equation so that we can simplify the solution for our problem. So if we are going to look at this equation right here, x minus 0. Now if we go back to this guy right here, so x minus 0 equation right here, if your x is greater than a or equal to a, you have this equation right here. Now if we look at this, if we go back here, it's x minus 0, which means that your x is always greater than 0, or at least equal to 0. It will never go to a negative number, which means that if we look at this guy right here, we are in this condition here, which means we can simplify this equation as just x raised to 1, or just simply x. So this guy right here, I could now change it into x. Note that this is not 0, it has a value of x. Now we look at the second term, x minus 1/4 L. This is a bit tricky because if we look at our beam, going to change color. So if we look at our beam right here, now your x at this specific point before your p, that's less than 1/4. So here, in this case, that's less than 1/4 in that region. It's more than 1/4 in this region after your p, which means this is difficult to evaluate, so we can leave this one as it is for now. Now we look at the third term, which is x minus L. X minus L, if you think about x minus L, this guy right here, x, it could change from 0 up to L. That's the whole length of your beam, which means that this x minus L, it's a negative number, or best case, it's 0, which means this guy would be 0 here. Eventually, we will have a simplified moment equation, which we can now define as mx is equal to 3p over 4. Now we have x, and then we have minus p, x minus 1/4 L raised to 1. Again, we eliminated the third term. We now have just two terms, which is this guy right here and this guy right there. Now we have mx, and our objective is to get the equation of elastic curve, which means we can solve this using the second order differential equation. So I could write this as EI d squared y dx squared is equal to 3p over 4 x minus p x minus 1/4 L raised to 1. Now I can integrate this function right here, so let's call it as, change the color to, let's use green this time, so that's equation 1. Now let's integrate equation 1. Now if we're going to integrate this one, so we're going to get EI. Now this becomes slope of your beam. That's equal to 3 over 8 p x squared minus 1/2, that should be p x minus 1/4 L now squared plus C1. So we have constant of integration C1. Now let's call it as our equation 2. Now we can further integrate this one because we are now using second order differential equation in order to get the equation of our elastic beam. I'm going to maximize this one. Oops, sorry. Maximize this. Okay. Let's go back. So again, integrate equation number 2, and then we're going to have EI times y is equal to, so now this becomes y, or deflection of your beam. It's 1/8 p x raised to 3 minus 1/6 p. Then we have x minus 1/4 L raised to 3. Plus now we have C1x plus C2. So we have two constant of integration. So we can call this one as number 3. Now we have C1 and C2. We can now apply boundary conditions. Again, take note that we integrated these equations right here by assuming that those are your variables. Okay. Now we have, sorry again. So we have C1 and C2. So C1, C2, and then we can get the values of C1 and C2 by applying boundary conditions. And if we look at our beam, what boundary conditions we can get? So flip here. So at point A, right here, point A, we have x is equal to 0. Your y is equal to 0 because it's connected right there. Same thing here, y is equal to L, we have y is equal to 0. So we can use those boundary conditions to solve for C1 and C2. So let's do that. So we have boundary conditions, so x is equal to 0, we have y is equal to 0. Or we can say x is equal to L, we have y is equal to 0. Apply boundary condition 1 and 2. So let's apply boundary condition number 1. Now for boundary condition number 1, x is equal to 0, y is equal to 0. So y is equal to 0, so we can apply it to equation number 3. So let's substitute that one to equation number 3. We don't have any other choice because equation number 2 you have slope. Equation number 3 has deflection, which is y, and then we have y is equal to 0 right here. So if we're going to substitute those numbers, it's ei times 0, and that's equal to 1/8 p0 raised to 3 minus 1 over 6 p. Now, this is our singularity function. First, let's substitute 0 right here, and then eventually we're going to evaluate the value. So that's 0 minus 1/4 L raised to 3 plus C1 0 plus C2. Now, change the color. So for sure, this is equivalent to 0. That's equivalent to 0. That's equivalent to 0. We are sure of that. So now we have to evaluate this function right here, which is your singularity functions. Again, how can we evaluate these singularity functions? It's not just taking this value right here and then getting a number. We have to look at the conditions here. So if we flip it right here, we have this guy here. Now remember this equation here, this one. So now we have, if it's a positive number inside or a 0 value, we assume that this would be x minus a raised to n. Now if it's a negative number, x minus a, if it's a negative number, we now assume a 0 value for our singularity function. Now let's look at our number right here. Sorry. So for this term here, this singularity function, it's a negative number, which means everything right here becomes 0. Now, based on this singularity function right here, we can say that our C2 is equal to 0. So that's going to be the value for our C2. How about for C1? We can apply our second boundary condition, which is x is equal to L, y is equal to 0. Now for this specific boundary condition, again, we're going to use equation number 3. We have no other choice because we want to use this y is equal to 0. So for equation number 3, that's ei 0, that's 0, is equal to 1/8 p L raised to 3. So now we have L instead of 0 minus 1 over 6 p. Now this is L minus 1/4 L raised to 3 plus C1 L plus 0. Now, okay, let's change color of pen to red. Now, we know that this will become 0. That's for sure 0. Now, this is 1/8 p L raised to 3. This is C1 L. Now, we have to evaluate what would be this singularity function right here. Now, going back to on how we evaluate our singularity function right here. So we have, again, this guy right here. So we have x minus a raised to n, and then again, if it's positive, we can change it into this form. If it's negative, we can change it to 0 value. In this case, it's a positive number. How can we tell it's a positive number? L minus 1/4 L, that's 3/4 L, which means this guy right here, we can now evaluate this one as 3/4 L raised to 3, and everything should be raised to 3. Which means I can now calculate for my C1 based on this number right here. Now, if you're going to interpret that equation, you are going to get C1 is equal to negative 7 p L raised to 3 divided by, sorry, it's not 3, that should be 2. Okay, let's erase that one. Okay, go back. So that should be raised to 2 divided by 128. So we have values for C1 and C2. So how can we get the equation of our elastic curve? So we have to go back to equation number 3 and substitute C1 and C2. So we have C1, C2, and then we have to substitute it to our equation number 3. Now, let's substitute that one. So we have EI, now we have Y is equal to 1/8 Bx3 minus 1 over 6 B. Now we have singularity function right here, x minus 1 over 4 L raised to 3. Then we have C1x, so that's plus. C1x is, so let's change that to negative because it's now negative. Now it's C1 that's negative 7 P L square over 128 x. So that's C1x plus C2, which is equivalent to 0. Which means that the equation of our elastic curve is this guy here. So you can just divide everything by EI, and then you will get the equation of your elastic curve. So that would be the equation of your elastic curve. Again, question here is, why do I have a singularity function right here? You cannot really simplify this one because the idea for the equation of elastic curve is the equation should describe the value from, if you have a beam, this equation should describe the deflection from 0 to x. And in this case, this singularity function right here changes, it depends on your location, which means you have to keep it as it is. So that's how we solve singularity functions. That's how we get an equation of elastic curve from your singularity function. Now, okay, I'll just minimize this one. Okay, so that's for this specific problem. So how about if we have something more complex? I'm not going to solve this one, but I would recommend you to look at it and solve it at home, but I'm going to teach you how to solve these types of problem. So for concept application number 2, so find the following. First, the equation of elastic curve using singularity functions. Letter B, its deflection at x is equal to 1.8 meters. So we have all the values here. So we have P, which is 1.2 kilonewtons. We have W naught, which is this 1.5 kilonewtons per meter. We have value for their moment. We have all the dimensions. Just going to drag my board here. Now, if I'm going to draw this beam right here, so that's A, that's B. Now I will just assume a force here, AY, and then you have your BY. Then you have moment here, which is M naught, and then you have a distributed load. And then you have your force, concentrated load P. Now what if I have that force and let's say I would like to get my moment equation? Why do I have to get my moment equation? Because I would like to get the equation of my elastic curve, which is the question right here, which means I could use my second order differential equation. So again, going back to that equation, d squared y dx squared is equal to m as a function of x over ei. So I would like to get m in terms of x. And how can I do that in terms of singularity function? I can look in the table right here, and then I will have a specific form of my singularity function. Now, based on this loading condition, I have how many different types of forces and moments? So I have one, I have number 2, label it 1, 2, I have 3, which is my moment, I have number 4, which is my concentrated load, and I have number 5, which is my distributed load. Now, the thing here is I have concentrated loads, which is AY, BY, and your P, which is not a problem. If we look at the table right here, concentrated load, sorry, it's not here. Yeah, oops. So here I have my concentrated load. I should not encounter any problems if I'm going to get my moment right here. So, okay, let's put back the board. Okay, however, so for moment, it's also not a problem because for moment, we also have equation for moment. So, sorry, I'm just going to drag it down. Oops. For your moment, so you have your moment, which is m, right here. So you have equation for your moment, negative m naught x minus a raised to 0. You have your concentrated load. How about for distributed load? If I'm going to drag my board right here, note that for your distributed load, it starts at point A, but it ends all the way through the end of your beam, which means that this table right here, it's not equal to this guy right here. How can I solve my this type of problem wherein I have distributed load somewhere in the center of my beam? In this case, you have to apply various loads that cancels out in order for you to use your singularity function. What do I mean by that? So if I'm going to look at this beam right here, change it to blue. So this would be your concentrated load. Sorry again. That's your concentrated load. Now I could add a force, which is this right here. And then I could add another force which counters the one I added right here. So you would imagine that these two forces right here will cancel out. So this guy will cancel out, and then this guy right here. Which means that if I'm going to add these two forces right here, I could use this form of my singularity functions. Again, I cannot use this one initially because my distributed load, it's in the center. It's not from A up to end of your beam. But now when I added a force, I assume that this force right here extends all the way through the end of my beam. And then I added a counter force to subtract this force right here. So now I'm going to get the same type of loading condition. Which means in order for me to solve this problem, I'm going to get a beam which would look like this. So now this one would be my distributed load. Now I have another force here to cancel out the force on top. I have AY right here. I have BY right here. I have P right here. And then I have moment somewhere there. So I think I have moment right here. So now I could now express this loading condition in terms of singularity functions. So I'm going to have 1, 2, 3, 4, 5, and then 6. I'm going to get 6 different terms for my singularity functions. And once I have m as a function of x, I can now use my second order differential equation. If we go back to the problem here, Okay. So now this is a problem here, and the only difference is we have these values, those dimensions. You can just substitute it at the end of the problem. So try this problem and see how this one works. And our next topic would be superposition, which is going to be the last topic under deflection of beams. So I'll see you on the next online lecture.